homework assignments. Flip through, see if maybe there was one that wasn't done or didn't have enough work on it. So the plan is, we've got a little bit of a short week here, but we'll probably finish 5-5 by Wednesday, and then Thursday maybe like a little in-class worksheet over 5-5 since we've got the long weekend coming up. But this section does introduce some new formulas to us, and the ones that we're talking about today are called the double angle formulas. And these are not on handy dandy, and so on a test or a quiz you would want to put these on your cheat sheet for sure. These are going to be very important. So they're actually over here too, but you can probably see them better on the smart board. The first one says sine of 2u equals 2 sine of u cosine of u. Sine of 2u equals 2 sine of u cosine of u. I want to point out real quick that the reason this is called a double angle formula is because of this part right here. Sine of 2u. Now, it's not always going to be u. U is the angle. So it might be theta, or it might be x, or some other crazy letter. But the main idea is this right here is what makes it a double angle. It's 2 theta, or 2x, or 2 times whatever the angle is. Now, with cosine of 2u, you can see this on the sideboard, but there's actually 3 different formulas that you could use. And so the first one says cosine of 2u equals cosine squared of u minus sine squared of u. And I'll go ahead and list out the other ones. And I'll try to kind of give you a good idea of when to use which formula. The second one says 2 cosine squared of u minus 1. And the third option says 1 minus 2 sine squared of u. No matter which formula you use up here for cosine, you should always get back the same answer. Now, I'll tell you what I usually do. If I'm ever asked to find cosine of 2 theta or 2x or whatever it is, I usually use the first formula. That's just the one, that's my go-to formula if I need it. But if there's something in the problem telling me I shouldn't use that, maybe I should use one of the other ones, I may have to use one of the other ones. And here's an example of that. If you're working on a problem that only has cosines in it, you might want to use the formula that only has cosine. Or if you're working on a problem that only has sine, maybe you'll want to use the formula that only has sine. Otherwise, like I said earlier, I usually just use the first one. But there might be times where that's not a good idea. Okay, and then last one, this is tangent of 2u, set up as a fraction, kind of like our sum and difference formulas were. It says 2 tangent of u divided by 1 minus tangent squared of u. So one option for sine of 2u, one option for tangent of 2u, but 3 options for cosine of 2u. Most of the time we'll just use the first one. Okay, now the directions and the figure are given here for the first, I think, 6 examples. It says use the figure, it's a triangle, use the figure to find the exact value of the trig function. use the figure to find the exact value of the trig function. And you'll see the triangle up here. It kind of looks like a triangle in quadrant 1. The bottom side is 7. The side opposite of theta is 3. Hypotenuse is not given to us, but more than likely we'll probably have to find that here in a little bit. Now, what's kind of nice about this lesson is that not all of it is going to be new stuff. If you look at example 1, all we have to find on example 1 is cosine of theta. It's not cosine of 2 theta, it's just cosine of theta. We can go back to our SOHCAHTOA days to do this. Here's theta. Cosine is adjacent over hypotenuse. And so according to our triangle, this is adjacent. Hypotenuse is what I don't know. So I'm going to show my Pythagorean theorem work off to the side here to figure out what the hypotenuse is. This is 7 squared plus 3 squared, or you could have that flipped, equals c squared. So this will be a 49 plus 9, which is 58. Then I square root both sides, and I really don't think you can break down the square root of 58. And you definitely don't want to use decimals because it says exact value. So we'll just leave the hypotenuse as the square root of 58. Now, when I go to do SOHCAHTOA, adjacent over hypotenuse, I don't want to leave my answer like that because it needs to be rationalized. Let's multiply by the square root of 58 on top and bottom, and I just get 7 square root of 58 all over 58. That would be my answer for number 1. I didn't even need one of those new formulas. Okay, let's keep going here. Some more old stuff for us. Number 2, tangent of theta. Tangent of theta. Well, theta's down here at the bottom again. Tangent is opposite over adjacent. We don't even have to rationalize that. That's just going to be 3/7. So there we go. Now, I'll just go ahead and tell you this while I'm thinking about it. The reason we're going back and doing all of those simple trig functions is because those simple trig functions show up in our formulas. Later on, when I do tangent of 2u, I'm going to have to know what tangent of u is. Or in our case, if I have to do tangent of 2 theta a little bit later, it's going to help that I already know tangent of theta because that will be part of the formula. So there's a reason why we're going back and doing all of this stuff. Okay, same triangle. I'm just switching over to a different problem. Number 3, sine of 2 theta. 2 theta. That tells me that I need to use a double angle formula. If you look at your formula, the u in this problem is actually theta. So it says 2 sine of theta, cosine of theta. Now I want to show you a little trick here, so don't work too far ahead. Work with me and then you'll kind of see why this is helpful. The 2, I'm just going to put that back out front for a minute, and then I need to plug in something for sine of theta and plug in something for cosine of theta. All right, so follow me. Sine is opposite over hypotenuse. Usually, I want to rationalize that, but let's leave it not rationalized, and you'll see why why that is going to be helpful. Let's leave sine as 3 over square root of 58. And I'm going to do the same thing with cosine of theta. It almost doesn't feel right to use a fraction that hasn't been rationalized, but you'll see here in a minute why this works. Cosine of theta, you can go back actually to what we did on number 1, but don't use that fraction. You could, but it will take a lot more simplifying if you use this fraction. Go back and use what cosine started out as, which was 7 over square root of 58. Now watch how easy this is. On bottom, this is just a 1, so it doesn't really matter, but square root of 58 times square root of 58, square root of something times the square root of the same something is just the something. If you plug in the fractions not rationalized, they kind of rationalize themselves, and you don't have a square root on bottom anymore. Now on top, this is 6. 6 times 7 is 42, so I get 42 over 58. I would want to divide by 2 on top and bottom to simplify that, but there it is. Okay, if I had used the fractions that were already rationalized, I don't know what 58 times 58 is, but that would be a really big number on bottom, and I would have a lot more simplifying to do. I could probably cross out a 58 once I multiply those together, but it gets a little messy when you do it like that. So I'm not saying it won't work, but doing it this way just seems to work out a lot nicer. Okie doke, any questions about what we did there? Go ahead. Yes, that is fine. Any other questions? Okay, let's keep moving. Number 4, cosine of 2 theta. Cosine of 2 theta. Look at all of our options up here. 3 options. If there's something in the problem telling me not to use the first formula, then I won't. But I don't think there's anything in this problem telling me otherwise. You'll see a little bit later in the lesson when you might want to use one of the other 2 formulas. But for right now, we should be okay with using the first one. Any of them would work, but this is usually the one I pick. Cosine squared of theta minus sine squared of theta. Now, remember that cosine squared of theta is the same as the entire cosine of theta squared. And same back here. Sine squared of theta is the same as the entire sine of theta squared. Now, I just need to plug in what those trig functions are, and then I should be able to simplify. But once again, I'm going to pick, or I'm going to use the fractions that have not been rationalized yet. For cosine of theta, you can actually go back up here or use the triangle. That was 7 over the square root of 58. Sine was 3 over the square root of 58. Now I need to square those fractions and then subtract. Okie doke, let me catch up here to the PowerPoint. When I square a fraction, I square the top and bottom separately. What do you get on bottom when you square the square root of 58? 58, yep, and then 7 squared was 49. Now kind of the same idea over here. When I square the square root of 58, it's just 58. and then 3 squared, that will give me a 9. Okay, now 49 minus 9, that is 40 over 58. We should probably divide by 2 on top and bottom to reduce that, but there it is, 20 over 29. Any of those formulas would have worked. Usually I just pick the first one unless there's something telling me that I shouldn't. Any questions on number 4? All right, we're going to try a couple more of these, and then we'll go back and do some equations to solve. But number 5 says tangent of 2 theta. Tangent of 2 theta. Well, this is it. This is the only way to simplify or to evaluate the tangent of 2 theta. It's got 2 tangent of theta all over 1 minus tangent squared of theta. So we found tangent earlier. You can reuse that answer or just go back to the triangle. Opposite over adjacent, that was 3/7. On top, you're going to be taking 2 times 3/7. On bottom, remember this is the same as the entire tangent of theta squared. So I'm going to write that as the entire 3/7 squared. Now, I'm just going to go on top here for a minute. The top part becomes 6/7. On bottom, I should probably square that fraction first. We can square the top and bottom separately. That'll turn into 1 minus 9/49. And I need to do a little bit more work on bottom before I can keep, change, flip. This is subtracting with fractions, so we do need to get some common denominators. Let's think of the 1 as 49 over 49. Then 49 minus 9, that is 40 over 49. So here comes the keep, change, flip. Keep the 6/7, change it to multiplying. I don't know why I was going to put 60 on bottom. That should be a 40 on bottom. And I probably could reduce those diagonals a little bit. Divide by 7 right here. That'll be a 1. That'll be a 7. Divide by 2 right here. That is a 3, and that is a 20. So 21 over 20. That would be my answer for tangent of 2 theta, 21 over 20. Okay, any questions about the steps that we did on number 5? Well, now that I had you do that, before I put number 6 up here, I want to show you something else that you can do to find tangent of 2 theta. If you want to just put this somewhere off to the side, you can, because actually it may have been a little bit quicker to do it this way. If you go back to your quotient identities, tangent is always the same as sine over cosine. And this is even true with double angles. Tangent of 2 theta would be the same as sine of 2 theta over cosine of 2 theta. Now I'm going to go back and get those answers from earlier. Sine of 2 theta, that was our answer from number 3. That was 21 over 29. Cosine of 2 theta, that was our answer to number 4. That was 20 over 29. So now, keep, change, flip. Keep the first fraction, change it to multiply. Flip the fraction on bottom. What do you know? That also gives us 21 over 20. The only time I wouldn't want to do it this way is if I'm working on a problem and maybe I haven't found sine of 2 theta yet. Or maybe I haven't found cosine of 2 theta yet. Then I may just go back and do it this way. But if you already know both of those, then it is a little bit faster to just do a quotient identity. Okie doke. So there's that, in case you can use that later. Now, last one of these that we're going to do says secant of 2 theta. Secant of 2 theta. Now, hang on, Mrs. Street. You didn't give me a formula for secant of 2 theta. I know sine, cosine, and tangent of 2 theta, but not secant. Now, what do we know about secant in relation to those other formulas? It is. Secant is the reciprocal of cosine. So I just kind of wrote a step up here in case you want to write this in your notes. Because secant and cosine are reciprocals, to figure out this problem, should be pretty easy, I just need to flip over my answer to cosine of 2 theta. Whatever my answer was from cosine of 2 theta, flip that over. Now, what was that? That was number 4. It was 20 over 29, so now it's just 29 over 20. Okie doke. If I didn't know what cosine of 2 theta was, I would have to find that first and then flip it over. But most of the time, that's something you did in an earlier problem. Any questions at all about using the double angle formulas? Okay, you'll see why in this next set of problems, why the formulas are really helpful. These are just kind of getting practice using them, but now we'll see how these can help us when we go back to solving some trig equations. Directions just say solve each equation. Now remember what we did with trig equations. Most of the time we want to get everything to one side. If we have different trig functions, we want to somehow make them the same. And then by the time we're done, we can use that table at the bottom of Handy Dandy to look up our answers. Okie doke. So here's number 7. Sine of 2x plus 2 cosine of x equals 0. Everything is already on one side. But what I don't like about this problem is that this has sine and that has cosine. It's going to be really hard to solve and really hard to factor if those trig functions are different. So there's not much that you could do to this term for cosine of x. You could use a reciprocal identity, but that's just going to be secant, which won't really help us. So I'm looking at this first term, and I notice the 2x. The 2x is what tells me it's a double angle. So why don't we replace that part in blue with 2 sine of x, cosine of x. It's a double angle. And now I'll just bring down the other term, plus 2 cosine of x, and it equals 0. So I still need to solve this, but anybody see what we could do next? Think about factoring. Yeah, they do both have a cosine of x in common. And actually, they have a 2 in common as well. If you wanted to pull out the entire thing, you could pull out 2 cosine of x and then figure out what your leftovers are. So divide by 2 cosine of x, and that drops out, that drops out. I'm just left with sine of x. And don't say everything drops out over here. You would still need the plus 1. All right. Now, zero product property. I want to break both of those apart and solve for x. So right here, we would actually need to divide by 2 first, technically. And then I'm looking on Handy Dandy to figure out where cosine is 0. So scan the cosine row, and I think you get back a 0 at pi over 2 and 3 pi over 2. So there's a couple solutions. Now on the other side, subtract 1. Now I need to know where sine is -1, and it's at 3 pi over 2 again. So you don't really have to write it down a second time. If you see it's a repeat, you can just leave it as this, pi over 2 and 3 pi over 2. Those are the only solutions to that equation. Okey-doke. Any questions on that one? All right, we're going to do just one more problem here. Number 8, cosine of 2x plus cosine of x equals 0. Now, before I do anything, I want to point something out to you. This is not the same as cosine squared of x plus cosine of x equals 0. If that was being squared, I could pull a cosine of x out front, and then everything would be great. I'd look them up on Handy Dandy, and I'd be on my way. But I was only allowed to pull that cosine of x out front because both of these had a cosine of x. This is cosine of 2x. That makes it not a like term with that. They don't have anything in common, but here again, I see the 2 with the x, and it makes me think of my double angle formula. So I'm thinking I probably need to rewrite cosine of 2x. Now, here's where we have to think a little bit. I probably don't want to replace it with that first formula because the first formula has cosine squared and sine squared. If you look at what you have in this problem, the only other trig function that you have is cosine. So you don't really want to use any formulas that would introduce another trig function, which means I'm going to probably replace it with the formula that only has cosine. And again, the reason behind that is you only have cosine in this problem. So it would make sense to use the formula that only has cosine. All right, so I'm putting in 2 cosine squared of x minus 1. And then you can go ahead and recopy the rest of it. Plus cosine of x equals 0. Now, I still can't factor anything out front, but there is a trinomial up here. You'll probably want to rearrange the order a little bit. Put the plus cosine of x in the middle and the minus 1 in the back. Now this is going to be factored using yucky factoring, but that's okay. It's kind of like 2x squared plus x minus 1. If I try to factor that real quick, 2x times x, signs are different. I don't really know where they should go yet. I'll just have to FOIL it out to check. And the only numbers that multiply to 1 back there are 1 and 1. But I think this is wrong, actually. I get 2x squared minus 2x plus x minus 1. That would make a negative x, and I needed positive x. So I should do the old switcheroo. If you're ever off by just a sign, then just switch your signs. Don't switch anything else, and that should work. Now that would give me a plus 2x minus x, and everything is good. So in our problem, we're going to factor it using 2 cosine of x minus 1 times cosine of x plus 1. It's exactly like this, but the x's turn back into cosine of x's. So we are factored. Now I should be able to break those apart and solve for x. Any questions about the factoring part before we finish this? Looks like you're all on it. So add 1, divide by 2. You'll be looking for where cosine is 1/2. And there's 2 places, pi over 3 and 5 pi over 3. Now, second part, subtract 1, and you're looking for where cosine is -1. I think that just happens at pi. Okie doke. Since we are learning these formulas today, for the most part, on the equations in your homework, find the one that has the 2 in it, and then replace it with one of your formulas. Okay, so here's the assignment. This is T43 from page 390. We're going to do 9 through 12, and then 14 and 16. I did put a little warning up there about number 10. Once you get that copied down, go ahead and open up your books, and I'll show you what I'm talking about there with number 10. I'll try and draw it up here. Maybe we can all look at it together. There is a triangle that you'll use on number 9 and a different triangle that you'll use on number 10. This, it's in your book, but this is what the triangle looks like on number 10. I said look out for theta on number 10 because we're used to theta being down here. That's what we had in our notes. Theta is actually up here on number 10. So when you go to do SOHCAHTOA, the opposite side is actually 12, and the adjacent side is 5. Okay, you always have to start where theta is, and theta just happens to be up here on number 10. So again, opposite side is 12, adjacent is 5.